Okay, so this was the setup from last Thursday, and I want to explain a little bit more about what it's doing. Now the picture is exactly the same as what I drew last time, except that this time I put a 1 here because I realized that putting a 1 here makes sense because this output A3 is multiplied by 1 and plugged into the cross entropy function. Okay, so see this A3 is not modified. So I'm putting a weight of 1. And I wrote down how the values A1, A2, A3 are calculated. For example, Z1 is the thing inside, and phi is the sigmoid function. I explained that sigmoid is something that goes between 0 to 1. And phi prime is equal to phi times 1 minus phi. That was another property. And so A1 is calculated by multiplying the inputs by weights. See, this node has 2 inputs, so x1 and x2 are both multiplied by weights, and you're adding a bias. And same thing is done for the other cases. For this last one, it has 2 inputs from A1 and A2. Those are multiplied by the weights U1 and U2, and its internal bias is C. And then what it does is, at the end of the day, when any 2 inputs, x1 and x2, are fed into it, it just calculates A1, A2, A3 in exactly the same manner, and then feed it into this value, where y is either 1 or 0. And the inputs are always a triple, right? x1, x2, and then y. These are the inputs, and this is the actual y that you want, following the XOR. So it's like 1, 0, it should be 1, and if it's 1, 1, it should be 0, and there are 2 other values I explained as a table. And because we've generated thousands of data sets like that by randomly choosing x1 and x2 values, so we had some values here, values here, values here, values here, and we wanted these 2 values to be 0, whereas these 2 values to be 1. That was what we wanted, the XOR. And then in the YouTube video I uploaded, I had 4,000 data sets. So what you're supposed to do is you should be feeding all those 4,000 pairs of numbers, and then calculate the output against the output that it should have. And that entire sum, this entire value, we're calling it as f. And then f is a function of, you could say that it's a function of W11, W12, W21, W22, B1, B2, U1, U2, C, and that's it, right? Okay. So these parameters. And at first it sounds a little bit weird because aren't you plugging in x1 and x2 to get the value of f? It is right, but what's happening is that we're fixing the examples. So 4,000 examples that we feed in will be fixed. And we're just going to tweak these parameters a little by little until this is minimized. And when it does get minimized, then this machine will be able to compute the XOR perfectly. Yes?
Let's say our neural network is much more robust or complicated than the one we have on the board.
Mm-hmm.
Would the function still be the same inside the sigma? Inside the sigma notation?
Yeah, this is called cross
The
entropy.
cross entropy?
Yeah, that's used for classification.
Right.
If you want to have a better prediction, usually people write down something, the different squares. They have different purposes.
No, I mean, if the neural network had more weights, or let's say more nodes,
Oh, yeah.
would the cross entropy change too much?
Yeah. So I'm going to talk about the monist. In that case, the final node is not a single number. It's actually a vector of 10 different numbers.
Mhm.
For that, the cross entropy will look slightly different. I'll show that to you. Okay. All right. So you have this, and now we calculated the partial derivative because we were supposed to move in the direction of the negative gradient, right? So that's what we did last time. Now, as you write down the partial derivative, you start seeing some kind of a structure. And what is that structure? The structure is that, see, this last thing, and by the way, when I was writing these formulas down, I forgot about the sigma because it's kind of linear. You can just calculate these and add them up. That gives you the grand gradient. So I'm just thinking of the derivative of this thing for a single pair of x1, x2 versus one single value that the output should have. So if you differentiate this function with respect to A3, this is exactly what you get. And then if you differentiate by this function by ui, let's see what that does. So u1 goes through A3 times the weight and then this, right? So it's the rate of change of the final function times 1 times A3, actually times, not A3, sorry. It's rate of change of the final function times 1 times oh, I just realized something. So this is a bit more complicated because see, the derivative of this is not really a3 minus y. Did I write y minus a3 or a3 minus y?
A3 minus y.
Okay. So a3 minus y, and it's really 1 minus a3 times 1 minus a3. Times a3 times 1 minus a3. Okay? And since these two are equal, we canceled it. But I like this format better because, first of all, this is the derivative of this one. And then times 1 times the derivative of this thing. That's what the error is. And that is the rate of change of f with respect to c. Because if you look at c, changing c affects what? Changing c affects a3, which in turn affects this final function. And if you look at the way that c influences f, it goes through, for c, it goes to a3, and a3 goes through 1, and then goes to the function. So what we are seeing is that you just have the derivative of this thing times the weight that was used times the derivative of this function, this sigmoid. That's what's happened. Right? Okay, and then when you read this, let's see how f is being affected by u1, and it goes like this. u1 goes through a3 and 1, and then this function. So this times this much is the error, right? And then it multiplies by a1 because a1 is the input. So I want you to think of this function. this formula in the following form. Derivative of f with respect to u1 is rate of change of f with respect to c.
Why is it U1? It says UI.
Yeah, I is like 1 or 2.
Oh, okay.
Yeah. So that's what it is, times input associated to U1. So the input that goes through U1 is A1. So that's what happened. This is A1. Okay. And you can write down the next one in the same manner. So let's think about W11. W11, how does this one affect F? It goes through A1, and then U1, A3, 1, and then this, right? So you see that derivative W11 is, first of all, this error times, well, this error is f with respect to c. So basically what this means is it's checking how much the f changes with respect to this guy here. Okay. Times the weight u1, because it went through u1, right? And by the way, this much was really how much f changed with respect to u1, right? So you can say how much f changes with respect to u1, and that's this much, times the derivative evaluated at the output, right? So this see, A1 is phi, sorry, that's not right. Phi prime, which is it's phi prime of z1, but don't pay too much attention to this one, okay? So this value right here, I'm just saying that this is the value of the derivative, okay? And times the input to this W11, which is x1, right? So we can see that there's a structure here, which is if you want to know how the loss function, this last thing is called the objective function or the loss function. If you want to know how the loss function changes with respect to the change in your parameter, you have to do the following. You have to multiply the rate of change of the function with respect to the weight after the next node, right? So it's this thing, times the rate of change at this node right here, right, by the activation function, times the input to that weight. That's how it works, okay? And that kind of allows you to be more flexible in writing other types of networks. So for example, what if we used ReLU? So what if we use ReLU? Well, ReLU is a function that's 0 before 0 and then 1 same afterwards, right? So for ReLU, if you differentiate ReLU, what would you get if x is less than 0? It's a piecewise function. 0, right? If x is bigger than 0, what would you get? 1. Yeah. So that's it. That's what's going to replace this one here if you're using ReLU as your phi.
Isn't that a ramp function? Isn't that the ramp function?
No, this one's called the Heaviside function. The derivative is called the Heaviside function.
Oh.
Maybe engineers call it ramp function? I don't know.
Signals and systems. That's
Oh, okay. Yeah. Mathematicians like to call it as Heaviside function. Heaviside. It's the name of a mathematician. Right. So that kind of tells you what to do for any kind of activation functions. I also explained the leaky ReLU, right? So leaky ReLU is if you have something small here. So let's say this slope is a lot smaller than this one, say like 0.1 or something, some very small slope, then this is going to change. Yeah. And I mean, the problem with ReLU itself is that once it's in the negative domain, this is completely turned off, so the parameters will be stuck. It wouldn't change. So sometimes that happens, and therefore you want to change that to leaky ReLU if you need. Okay. So that's one thing. And then once you see the structure, now the point is that you can see that it follows some pattern, so you should be able to write a package where you don't have to do all these calculations. Okay? And that calculation feature is called an autograd. So it's called an autograd. And what autograd does is it knows the function and its derivatives for various predefined ones. And if you want to make your own, that's fine too. You can make your own. And if you want to make your own, then you just have to define it, and you have to tell the software what its derivative should be. Okay? So once you calculate these and give it to the computer, the package, then it will just do all these calculations automatically because it knows exactly which place the derivative should be put in. Okay, and that's what popular neural network software does. So there are two very popular ones. So there's the PyTorch and then TensorFlow. PyTorch was developed by Meta, Facebook, and TensorFlow was developed by Google. And then there was a separate package, and there were many others. Like for a while, Cafe was pretty popular as well. I'm not so sure about the spelling. Now they don't use it as well. Now they don't use Cafe as much. There's something called Keras, which was a separate package that were made because TensorFlow was somewhat hard to make and hard to use. And later, TensorFlow teams looked at Keras and said, hey, this is so nice. Can we just have it included? So now Keras is included in the TensorFlow. So these packages, PyTorch and TensorFlow, are good because of two things. One is that it does the autograd, so you don't have to think about all the chain rules, so it's a lot faster. Second is it also has different optimization algorithms. So here I only gave you just the gradient descent, right? So I just gave you the gradient descent. But then people realize that you don't really have to do all the summations. So instead, what they do is they would see. In my YouTube video, I had 4,000 inputs, right? So out of the 4,000, you don't have to use all 4,000. You can take this into batches. So if my batch size is, say, 128, then it won't process all 4,000. We'll just take 128 samples from the 4,000 and add up this much to compute the gradient, which is not the perfect gradient, but it's good enough because this 4,000 is shuffled up, so it's good enough. And then, so you just get chunks of 128, calculate this, do the gradient descent, and then you keep going. And that kind of gradient descent, because you're just sampling and then taking the gradient descent from there, that's called stochastic gradient descent. So you usually, SGD would be the acronym that people use, and I think the naming is just made to scare off people. Like once you hear something called stochastic, it sounds really, really hard. But it's nothing. It just means that you're taking batches and then taking gradient descent. And then you just do this repeatedly. So you do that, and then eventually, yeah. So you have that optimization called stochastic gradient descent, but then people change this a little bit. So there's like an adaptive momentum model called ADAM. That's actually the one that's most popular, and there are several other kinds of optimization schemes in there. It also has predefined functions for different kinds of machine learning layers. So right now what I'm showing you is just something called the dense layer. Dense layer is it's when the next layer is connected to every input in the previous layer. That's called the dense layer. But there are several other kinds of layers defined in these PyTorch and TensorFlow. What else is good? Oh, and the most important thing is that these can make use of GPU. Now, what's the difference between GPU and CPU? Do you know?
GPU focuses on video graphics.
Yeah, I was originally made to do graphics, but then at some point, some computer science graduate student realized, well, I guess he was a gamer, I don't know. But yeah, but he realized that the GPUs work very well because it's made to handle lots and lots of calculations that are simple, done at the same time. So what happens is that GPUs have something called shaders. So in CPUs they have something called threads, right, or cores. So you might have a CPU in your computer that has 4 cores, or some good ones will have 8 cores.
16 we have.
You have 16? Some of them have 16. Yeah, so that means you can have 16 cores means you can have 16 calculations processed at the same time. What shaders does is shaders are tiny little cores, which is quite dumb because, for example, it has a command base where everybody in one of these shaders has to do the exact same calculation. So if the main guy in the shader says multiply, then everyone that belongs to this shader has to multiply. Everyone does addition. And the commands are very limited. The CPUs have many different instruction sets. GPUs have very simple instruction sets, so they're very simple. But the power of the shaders is that when you're playing games, anytime you turn around, all of the things in the screen are what? Those are polygons, right? And those polygons, they have to move to the right place so that it looks like a 3D. It's not really 3D, it's 2D, but It has to look 3D so you can play your game, right? And that takes a lot of calculations, but the calculations involved in those calculations are pretty much the same. It's basically matrix multiplication, lots of multiplication addition. And then people who are doing machine learning research realize, well, if you look at what we're doing here, it's lots of multiplications and additions, right? That's all we are doing. So if that's what we are doing, why not make use of GPUs? Maybe that's faster. And that made a world of difference. So I think the actual neural network became, suddenly changed the world. It started in sometime like 2012. Before that, people were only programming in CPUs, and these things were so slow, they couldn't have lots of layers, they couldn't do anything powerful. But once they started making use of GPUs, they were able to train the models that are much, much bigger with reasonable amount of time. So that's why by year 2017, there was the AlphaGo that shocked the world, and the rest is history, right? So that's the important thing. Making use of GPU is quite tricky because GPUs have their own language system, and therefore having PyTorch and TensorFlow do the GPU part for you, that's also very powerful. So that means if you're really going to use any of the neural network for real-world purposes, you probably want to use either one of these two. That's why I want to show you the TensorFlow today, especially the Keras one, because this is the easiest one to access. The other parts become quite hard quite fast. Another thing I want to say is that when I give you the demonstration, it has to be on Google Colab because many of your computers don't have a GPU. Some of you might. I see some gaming computers here. But even if you had them, you have to install the something called CUDA, and these things require special installation. It takes a while to install. So we're just going to use Colab because Colab was made to educate the mass about the neural networks, and therefore when you run any Colab instance, there's a, I think it's a P100 GPU that would be on, and the TensorFlow is already installed there, so it's a lot easier to use. Okay?
Is it in a virtual machine with Colab?
Yeah. So. Yeah.